All right, so we started on waves. Let me go back to it. What's a wave again?
Movement. Method of energy transfer between 2 points without particles traveling between.
Perfect. Method of energy traveling from point A to point B without particles traveling between the two. All right, that is what a wave is. And I told you there are two types of waves: mechanical and electromagnetic. And I think I gave you some more information. Electromagnetic, there is no need for medium. No need for medium. And it is electric and magnetic fields. Basically, they are electric and magnetic fields. And both are perpendicular to each other. So this is how it goes. The electric field goes like this as a wave, and the magnetic field goes like this, perpendicular. It's not easy to visualize it. It's like this is one set of waves, which is electrical, and the other one is magnetic. That's a magnetic one. Can you visualize it? Like one wave going this way, and the other wave going.
Oh yeah.
Can you?
Oh yeah, I've seen
Can you? Okay, that's good.
I know.
So one is going up and down like this. The other is going horizontally. Okay. So that's how an that's how an electromagnetic wave. That's okay. Got it. That's how an electromagnetic wave is, and no need for medium. Travels best in
Vacuum.
correct. Travels best in vacuum. At 310 power. At 3 times 10 power 8 meters per second. That's how fast the electromagnetic waves travel. Can they travel through solids, liquids, and gases? They can, but they'll be slower. Okay? They'll be slower. In gases, they can be as good as in vacuum, almost. But in liquids, they'll slow down. In solids, they can slow down almost to half of that number. It still is fast, but it is slow. Is that clear? And I told you this, comparatively, this one needs a medium. It needs something. It needs solids, liquids, or gases, something to pass through. And through gases, it cannot travel that fast. Through liquids, it can travel faster. Through solids, it can travel the best. So, okay? However, this is not as fast as that. This is actually on the slower side. To give you an idea, through air, let's talk about sound. Air, sound traveling in air is like 340 meters in 1 second. 340 meters per second is the speed of sound in air. So when I'm talking to you, the sound that's coming to you is coming at that speed, which translates to a mile in 5 seconds. So you can compare it now, right? This is not easy to understand, but this is easy to understand now. 1 mile in 5 seconds, that's how sound travels. Say, for example, you see lightning. And if the lightning is exactly 1 mile away from you, you will get the thunder. You will hear the thunder 5 seconds after. Get it? Now, if it's only half a mile away, 2.5 seconds after. The closer this time is, the more in danger you are. Okay? So if a lightning and a thunder kind of almost is simultaneous, then that means it is pretty close. Better do something about it. So 1 mile, 5 seconds, that's how slow sound is. Sound is really slow. Yeah.
How far does it go till it dies off and you can't hear it?
Sound? It depends on how much energy is being absorbed. Technically or theoretically, if I clap like that, this clap sound is supposed to keep traveling. There's no stop to it. It's even supposed to reach downtown. It's supposed to reach downtown, but then the intensity keeps going down, down, down. The energy is going down all the way. There is a minimum amount of energy needed for your ears to detect the sound. Okay, so if the minimum intensity is not there, say for example, if I drop this tissue and see if you can hear the sound of this tissue drop, you don't hear it because it produces such a small amount of energy, of vibration, which does not even, I mean, it comes to your ears, but your ears are not sensitive enough to hear it, especially yours, Nick.
Why?
Because you keep putting all those unnecessary stuff into your ears and pumping
Why
music.
me? Everybody does.
No, you better not do it because the more you push music into your ears and like play loud music into your
What?
ears,
Exactly.
that's what will happen. So the more you put into it, your ears will actually get immune to, it'll get used to the heavier sounds, so smaller sounds won't be audible. Now, it won't be understood until it is too late. Like it's a slow thing. Just playing some music now won't actually make a difference straight away. But what I see is that you have been already practicing for a long time, playing music into your ears. Occasionally, it's fine. I'm not saying it's like totally wrong. But try not to torture your ears, and then your sensitivity will be much better even at an older age. Even the tiniest sound will be audible to you at an older age. Now in the next class probably I'll test each one's hearing.
Let's go.
Yes, I will test each one's hearing and I'll find out exactly whether you're hearing this frequency or not. We'll check it out. So anyway, what I'm trying to say is this. What?
What?
Okay. My point is clear. If the energy is strong enough for your ears to hear, you will hear it. Otherwise, it's kind of gone. So what I said is this clap goes even to downtown, right? Yes, it can go to downtown. If there is no block and all that, it can go down to downtown. But then there are much bigger sounds by traffic and other things. So therefore, this sound is not going to be heard at all. Okay? Through liquids, through water, sound, this is through air. Through water, sound can travel 1 mile in 1 second. So it's faster. Sound is able to travel faster in water. So underwater, if you're underwater and someone actually creates some sound underwater, that will reach you faster. You can see that. 5 times faster. Almost. These are rough numbers. Through solids, like steel. Through steel, it can travel 3 miles in 1 second. So sound travels pretty fast in steel, 3 miles in 1 second. So you know approximately what is 3 miles, and it takes only 1 second for it to come. A good way of comparing is this. Imagine there is a railway track, which is made of steel, obviously, and suppose, imagine there's no other sound to bother you. It's all quiet, and let's say there are no trains. You put your ears on the track, and of course, if there are trains around anywhere a couple of miles away, you will hear some sounds in the track of the train, and therefore you can understand that you are not doing the right thing. Okay, so if you put your ears and listen to it, and let's say your friend is 3 miles away on the same track, 3 miles away on the same track, he has a hammer and he's going to hit the track. So when he hits the track over there, 3 miles away, and you put your ears on this side, how long will it take for you to get the first report? 1 second. And the second report comes through air after 15 seconds. So you can see the comparison. Through steel, it can travel really fast. Through air, it is not traveling that fast. What about in vacuum?
It's I don't know.
You never hear.
Fastest in vacuum. It needs to be.
No, yeah.
It needs a medium. In vacuum, sound cannot travel. It needs a medium. It needs something to pass on the energy. So sound cannot travel through vacuum. All right, so you got an idea of the speeds of the waves. And that, of course, is traveling with the speed of light. Now, I told you electromagnetic waves are split up into radio, micro, infrared, visible,
UV.
and then comes UV, and then comes X-rays, and then comes gamma. That's this is called the electromagnetic spectrum. Now, deliberately I've made this a narrow region because that is how it is. This is violet, and then this is red of the spectrum. So violet, indigo, blue, green, yellow, orange, red, all the colors. And it takes only a narrow region. So all that your eye can detect is only this section. Your eye cannot detect any of these. Okay? So you cannot, your retina cannot detect any of these things. But of course, they can create consequences. They can really create consequences. These can create consequences. In fact, this is the high energy area. So more energy, least energy. Least frequency, most frequency. In terms of frequency, most frequency, least frequency. Okay? So this whole thing is called the electromagnetic spectrum. So on that scale, violet has got more frequency than red. So violet has more energy than red. You get it? A blue flame versus a red flame, which is considered to be hotter. Blue flame. So you can see that comparison there. More energy with the violet, less energy with the red. Okay? Now, I told you the many places where these are all applied. Radio waves, television and radio signals and all that. Microwaves used for cooking and for cell phones. Infrared for remote controls and for infrared cameras and for infrared physiotherapy and all that stuff, like for some heat radiations that's used. UV is used for killing germs because it can kill cells. You can actually use it for killing germs and all that stuff. Medically, they are using it for that purpose. Well, it can kill cells as well, our body cells. That's what is used in tanning beds. Okay. X-rays has its own use. Gamma rays, chemotherapy, cancer treatments, burning cancer cells out, and all that stuff. So this is the whole electromagnetic spectrum. Now, which one travels faster, radio waves or gamma rays?
The same.
The same. They all travel with the speed of light. This is the whole electromagnetic spectrum. Radio waves to gamma rays, they all travel with the same speed of 310⁸ meters per second only in vacuum. They will have the same speed only in vacuum. But if this whole thing is going to enter water, which one will be slowing down more? What do you think? Like when this whole thing enters water, and now it's going through water, not through vacuum, they'll all be slowed down. They will all be slowed down. But which will slow down most? It's gamma. Gammas will slow down more. Radios don't slow down that much. They all slow down, but then radios will slow down less. Gammas will be affected more. Is that clear? All right, so the same with here. Like violet is going to be affected more than red when it enters the medium. But if they are not entering the medium, if they're going through a vacuum, they all are together. Is that clear? Yes. So that's the electromagnetic spectrum side of it. Now here, I told you it needs a medium. In solids is better, faster. Liquids and gases. Now, mechanical waves are classified into two. One is transverse and the other is longitudinal. Two types of mechanical waves. Two types. Transverse and longitudinal. Transverse and longitudinal. And on that side, electromagnetic waves are only transverse. So the two types of mechanical waves are transverse and longitudinal. Electromagnetic waves are only transverse, always transverse. Well, what is transverse? The word transverse, waves. When the particles are oscillating up and down like this. When the particles are tossed up and down. When the energy goes forward. Energy is moving forward, but particles are moving up and down. So particles bob up and down. Like if you take a rope, I'm pretty sure you've tried all this. If you take a long rope and hold the rope and then just do like, go up and down. If you take a rope like that and just, well, this is not a rope. But if you take a rope and just go up and down like this, right? You'll see that kind of formation. That is transverse wave. Transverse wave, what is happening is I'm holding the end of the rope here. The end of the rope that I'm holding is going up and down with me, right? In simple harmonic motion, up and down. But the neighboring particle is also going to go with me because I'm dragging it. But there will be a time delay. And that is how we end up having the transverse wave go like this. And I'll quickly demonstrate that one here. Here. Yeah, so imagine these yellow dots are the particles of the rope. These yellow dots are the particles of the rope. Okay? So if I'm going to hold this side and then go up and down, simple harmonic motion. And you can see what happens to the wave itself, energy itself. See? So energy is going forward. Energy is going forward. But did the first yellow dot move this way? It's only going up and down. Each yellow dot representing the particles of the rope is only going up and down. It's not going sideways. But what is going sideways? The energy is going sideways. So when I send the waves from here, energy is going this side. Is that clear? What kind of a wave is that? Transverse wave. Now comparatively, what is longitudinal wave? Longitudinal wave is when you have particles moving forward and backward. Particles are going forward and backward like this. So each particle is going forward and backward. And which way is energy moving? Energy is moving one way. That is called longitudinal waves. Now if I hit this one side like that, you will see something is moving, but it's not. You can see something is moving, right? When I hit here, you can see something is moving over here. Now what's happening is When particles keep moving forward and backward, it forms areas of compression, compression, compression. Can you see that area of compression where the particles are kind of moving towards each other? And then there are places of expansion, expansion, where particles are moving away from each other. Particles going towards each other, particles moving away from each other. So this is what is known as longitudinal wave. So on a slinky, you'll see compression as when the slinky is all collected together. That's when you'll see this. So when the slinky is coils are all touching each other, sort of. So this is expansion where the particles are moving away, and these are all compressions, compressions, compressions. Is that clear? In a transverse wave, we call this crest and trough. Crests and troughs. Crests and troughs. Some books say hills and valleys. That's not the right term though. Some say peaks and valleys. But most books will be using crests and trough. So you have crest, trough, crest, trough. Whereas here, it is made up of compression and expansion. Compression, expansion, compression. Is that clear? So, two types of waves. One is transverse, the other is longitudinal. Transverse wave is when particles move perpendicular. You can write that down. Transverse wave when particles move perpendicular to the wave direction. Transverse wave is when particles move perpendicular to the wave direction. And longitudinal wave when particles move parallel to the wave direction. They move parallel to the wave direction like this. Right, all those points, they're all simple to understand. Jack, come here. Neat. Yeah. And you stand here and hold this, like hold it together. Like that. No, like that.
Okay.
Okay. So to demonstrate the transverse wave, I can actually like move my hand up. You don't have to do any movement, okay? No. Can you collect a little more together towards you? Yeah. So now to demonstrate transverse waves, all I have to do is like move up and down like this. So what do you see is a transverse wave. Particles moving up and down where the energy is going forward. Now why do you see the energy is bouncing back from there? That's called
Extension. Or no, that's
reflection, right? That's called reflection. Now, if he was not there and if this slinky was forever like this, when I did that, it should have kept going. It should have gone. But now it's bouncing from his hands and coming back to me, and that process is called reflection, like echo. Is that clear? Now, so what you saw there was transverse. Up and down is transverse wave. Now, I'll show you the longitudinal wave. Just watch this. It's difficult to send longitudinal waves because it's forward and backward. So it's basically like, it's something like that. But it won't be easily noticed by you. So what I'll show you is just, I'll create a pulse. So I've created a compression here. Camera, can move a little more backward. Jack, move back a little bit, okay. I'm going to release this compression and just watch how the compression is pushing all the slinky coils, and you can see how the compression is actually pushing itself forward and how the compression is traveling to his hands, and it'll bounce back from his hands also. Watch. You see the compression moving back and forth?
That's kind of sick.
And you can feel it also when it's coming to you, right?
Yeah.
You see it? Yeah, it's a compression that's going forward and backwards. So that's a kind of longitudinal wave. Here. Okay, like this.
Yeah.
I'll call you back again soon.
Alright.
Is that clear? Transverse and longitudinal, two types of waves. And why we call this one as transverse is because the electric fields and magnetic fields are variation of electric and magnetic fields are positive, negative directions. That's why. Now, transverse and longitudinal waves are both classified. They are both classified into two more types. Yeah, both of these are classified into two more types, which is progressive and stationary or standing. So progressive and standing, those are the two kinds of waves. So how many different kinds of waves are there? Different kinds?
6.
4. There are 4 different kinds of waves. You can see it very clearly. Transverse progressive. We have transverse progressive. We have transverse standing. We have longitudinal progressive. And we have longitudinal standing. There are 4 types of waves. And over here, this is transverse and standing. Because the electric and magnetic fields are just stationary. They're not actually like, there's nothing that's traveling. So over there is transverse and standing. Transverse and standing is electromagnetic. But there are 4 different types. Now let's look at each one. What is a progressive wave? Progressive wave is a wave that progresses and moves in one direction. Like if Jack was not standing there holding it, that wave would have continued, right? That is a progressive wave. Is that clear? Progressive means going forward, just keeps going. Standing wave. Standing wave is something that's formed when, okay, can you write down the definition of standing wave? That'll be easier. Write down the definition of standing waves. When two identical progressive waves meet, it forms permanent positions. Of zero disturbance, permanent positions of zero disturbance, called nodes. It forms permanent positions of zero disturbance called nodes and permanent positions of maximum disturbance like here and called antinodes. So what is a standing wave? When two identical progressive waves move in opposite directions and meet, it will form permanent positions of zero disturbance. Look at this. Zero disturbance, zero disturbance, zero disturbance, zero disturbance. Called nodes, and maximum disturbance areas called antinodes. Is that clear? That is called a standing wave. So you have progressive wave, which is wave continuously moving forwards. Like if you take a rope and just keep bobbing the rope up and down, you get that way. You can come back again. Jack, you can come back
Oh,
again.
yeah.
same wave? No? All right. Now you don't have to do anything because, all right, so what is standing wave? When two identical progressive waves meet, right? So basically it's like he's supposed to generate a progressive wave and I'm supposed to generate another progressive wave going this way. But it should be identical. Now to avoid confusion, let me ask him not to do anything at all. We'll just look at the reflected wave because the reflected wave is exactly identical to what I produced. So I'm going to send waves from here and he's just keeping quiet. So can you raise your hand up a little bit? Yeah. So I'm going to send waves and he's just going to bounce it back on and you'll see how it forms a standing wave and you identify which is a point of a node and antinode. All right? There it is. That's a standing wave. Is there a point on the slinky which is not moving up or down?
Yes.
Can you see that spot?
That's a node.
That's a node. And this is a node. That is a node. This is an antinode here. And there is another antinode there. Is that clear? Now it depends on the frequency of what frequency I'm using. Now I'm going to use a higher frequency and see what happens when I use the higher frequency.
There's two places.
Yeah, now you can see the node is here and there's another node over there. You see? And there are three antinodes. There are three antinodes, one here, one middle, and one there. Is that clear? That is called a
Standing wave.
standing wave. And this kind of a standing wave can exist in different places. Now let's look at some of the examples of this. What is an example for a transverse progressive wave? Transverse means up and down, and progressive, going forward. Transverse and progressive. Cool? Transverse and progressive. Tell me an example. Yeah.
Is it a tsunami? Where is that?
Tsunami actually is any water wave is actually. Tsunami is a different kind altogether. But just simple example, ripples on water. You don't have to go that far to tsunami. Ripples on water. If you drop a stone into water, you will see the ripples. And the ripples are transverse because it's going up and down and the energy is going forward. The water is not moving forward.
What about shaking a blanket?
Yeah. When you do that, it's actually a transverse wave. So you can write examples here as waves on ropes, or waves on water. Can you write that example down for transverse progressive? Example for transverse standing. Example for transverse standing. Here is another example. This is on a string, and this is a tuning fork which can vibrate. And I'm going to make it vibrate. You see the standing wave there? On this. It has to spark. You see it, right? Okay. That's enough for you to see. But now, tell me an example of transverse standing. Example. It should be transverse and should be standing. Like here. Yeah. This is it. You don't need all that stuff. Here.
Like plug in a guitar string.
It is. All stringed instruments. Plucking a guitar string. So that is transverse and standing. Write it down. This is transverse and it is standing. You can see clearly there's a node here, there's a node there, and the middle is an antinode. Right? That is plucking a guitar string or any stringed instrument. Violin, piano. They're all stringed instruments and they're all transverse and standing. Clear? Longitudinal and progressive. Example. Example of longitudinal and progressive. Longitudinal and progressive. Longitudinal and progressive. Example. Throw. All right. Transverse, longitudinal and progressive. Example of that. It should be longitudinal in nature, which means particles should go like this, and it should keep progressing. What was the example you said? Sound. How are you hearing my talk? Is because of this. Because when my vocal cords are shaking and creating a vibration, creating a compression and expansion like this in my mouth, and that is passed on to the neighboring atoms, and that's passed on to the neighboring atoms. So basically the atoms are shaking like this. You don't see it because it's invisible. It's shaking like this. And finally, the particle next to your eardrum also shakes like that, and then it pushes your eardrum, and then your brain senses reception of the signal. So when I do that, and you heard it, that means I've shaken your eardrum. You get it? So what kind of a wave is that? Longitudinal and progressive, means continuously moving on and on. And the longitudinal standing wave, again, it's kind of difficult to visualize. Longitudinal and standing is when you have a longitudinal wave going forward and then it bounces off and then comes back to create a standing wave, which is supposed to be nodes and antinodes, which is difficult to demonstrate, but I can show it to you. I can show it to you. See here, this is a tube. I am going to send some waves from the top down into the tube. What will happen is the waves will actually bounce back and then come back and set up a standing wave in the tube. Well, you can't see the standing wave, but definitely you'll be able to hear the standing wave. Good morning. So that's a standing wave. Just a pen cap. So what happens is the frequency, one of the frequencies that I was disturbing here with, went down, came back, and set itself perfectly into a standing wave, and that is what amplified the sound. Now, if I'm going to use some other tube which is smaller, like that, then it'll be higher pitch, higher frequency. That's also standing wave.
So good an example.
Or if I have to do this, this is a longer tube. See? And so you're expecting to see what? Hear what? Lower pitch. You heard it, right? That one. That's a lower frequency. So now tell me, longitudinal standing waves, where are they used? Whistle. All wind instruments, flute, clarinet, saxophone, trumpet, church organ pipes. Can you see the pipes there in the church? Yeah. What's a pipe? That's exactly what it is. So longitudinal standing waves are all wind instruments. Simple. All wind instruments. This. Now, in a flute, how do they change the frequency? They change the frequency by changing the length. By closing the holes and opening the holes, they can actually change the length of the tube that actually is resonating. And that's how they make it. All right? Any questions here right now? Now let's go into transverse wave again, or waves in general again. So I gave you all the 4 different types of waves, and I showed you what is a standing wave as well. And you know the example of each one. So this is typically a wave. That's a crest, that's a trough, crest and trough. When I move this up and down in simple harmonic motion, the energy is going to be traveling to the right. Energy is going to move to the right. And now we need some definitions here. The first definition is called wavelength. The symbol for wavelength is not L, it's lambda, which is a Greek L. Lambda. It's a Greek alphabet. It's primarily used for wavelength. So nobody uses L for wavelength. It's always lambda. So how do you write lambda? You can see that. It's just like how you write X. You know, you go like that, and then you go from here down this way, but you start going from here, from the middle. Don't call it anything else like inverted Y and stuff like that, because this is something that you will end up bumping into at a later stage. If you may have to use the term wavelength somewhere. And when you have to use the wavelength somewhere, and if you tell someone it's an inverted Y, that makes no sense. So call it lambda, and it is the wavelength. And what's the definition of wavelength? Write down the definition. It is the distance traveled by wave in one time period. The distance traveled by wave in one time period. That is called lambda, the wavelength. And what's the definition of time period? Which I gave you earlier. What is the definition of time period? You have it already. Time taken for one complete oscillation. That means how long does it take for this first particle to go up, down, and back? That is called time period. And by the time I move this up, down, and back, how far does the wave progress? That is exactly a wavelength. So by the time I do this, the energy would have gone till here. Make sense? So this is called a wavelength. From here to here, that is a wavelength. So this is a wave. What you see here is a complete wave. Like in math, you say sine wave. Right? Sine wave. It's a wave. So this is one wavelength, and this is a second wavelength. A wavelength also is the distance from one crest to the next crest. And wavelength is also the distance from one trough to the next trough. Wavelength is the distance from one point to an identical point. Does it make sense? Wavelength is the distance from one point to an identical point on the wave. Successive identical points. So from one is here, The other is here. The other is here. So if you look at identical points, this is one identical point, this one is identical point. So any distance between two successive identical points is actually a wavelength. So what does this mean? It means lambda meters, it can travel in t seconds. Lambda meters, it can travel in t seconds. It can travel lambda meters in t seconds. Which means in 1 second, how many meters will it travel? If it can travel in t seconds, lambda meters, in 1 second, how many meters can it travel?
1 meter.
1 times
1 meter.
or t times.
$10, 5 cakes. $1, how many cakes?
Or
1/2. Now see, when it comes to cakes and dollars, you get it so quickly. Again, $10, 5 cakes. $1, it's 5 divided by 10. So, t seconds, lambda meters, 1 second. Lambda over t meters. Does it make sense? In t seconds, lambda meters, Cole. Oh my gosh. I need another projectile. Or the stapler, yeah. Alright. So in t seconds, it travels lambda meters. In 1 second, how many meters can it travel? Lambda over t meters. Now, tell me, what is that you know? What is the thing that you know? Distance traveled in 1 second. What is it called? Distance traveled in 1 second. You did it in first semester, the first things you did. Huh? Distance traveled in 1 second. How much distance does your car travel in 1 second? Tell me what it is.
Or velocity.
Velocity or speed. So, lambda over t is velocity of the wave. How fast is the wave advancing? It is lambda over t. An important equation. Lambda over t is velocity, a simple, easy to understand equation there. What is the reciprocal of time period?
Time
Time
over.
over.
Yeah, 1 over time period. What is that? No. Just tell me what is 1 over t? Frequency. 1 over t is frequency. And therefore, I can remove the 1 over t from this equation, and I can rewrite this equation as v is equal to f lambda. This is a well-known equation in waves. This is called the wave equation. This is called the wave equation. And this is true for any waves, whether it's light waves or sound waves or mechanical waves or any waves, this is true. Velocity is frequency times lambda. And velocity of a wave depends on the medium. Velocity depends on the medium. But frequency and lambda are inversely proportional. Frequency and lambda are inversely proportional. When one goes up, the other goes down. You can see this. One wave is going like this. And the other wave is going like this. Which one's frequency is more?
The top one.
Which one's wavelength is more?
Bottom.
You see that? So the speed is the same. So velocity is equal to frequency times smaller lambda. And here velocity equal to frequency times a bigger lambda. Does it make sense? And I can show that here. I can show you the standing waves right here. You can see the standing waves. You can see some points are not moving and some points are moving really well. You see it? Do you see some points are not moving at all?
Yeah.
Yes? That's a standing wave.
Look at the ones in the middle.
Some of the ones are not moving and some of them are really crazily moving.
The ones that aren't.
That's a standing wave. But alright. Now watch out this. I'm showing you these two. Both travel at the same speed. I'll show you the smaller frequency, bigger wavelength. Smaller frequency, bigger wavelength. Can you see the bigger wavelength here? Like distance between the peaks. Just look at the distance between the peaks. See? And now I'll show you the other one, which is higher frequency and shorter wavelength. It's the same speed, but you can see when I increase the frequency, you can see there are a lot of peaks close together. So this is exactly what you see.
Do super high, super fast.
No, the speed is the same, whether it is this or whether it is that. Speed is the same. Speed depends on what? It's like this one depends on what? The medium. Like this one is steel in between, so that's the medium there. If I'm talking to you, speed is not affected by how I'm talking. Like for example this or this has a higher frequency. Which is a higher frequency? This one is a higher frequency. So the compressions and expansions coming to your ears are close together because of the higher frequency, like this. You get it? Whereas this one is a low frequency. That means it's this type, where the compressions and expansions are further separated. But the speed is exactly the same. Speed of sound in this room is 340 meters per second. That's not going to change. Do you understand the wave equation? So, if I'm going to give you an example right now, if I'm talking with a frequency of 680 hertz, if I'm talking with a frequency of 680 hertz, which is almost the frequency of the bell sound, you know. Imagine I'm screaming at that pitch. What is the wavelength? If I'm talking at a frequency of 680 hertz, what's the frequency? What's the wavelength? 1/2. Exactly, because if you plug into this equation, velocity is 340 is equal to frequency 680 times lambda. So the wavelength is going to be 1/2, which is this much. So one compression is here, the next compression is here, the next compression is here. You understand what I'm saying? Right? And the same applies to the light. In light, V equal to F lambda applies there, but instead of using the V, they use the expression C, because speed of light is a kind of constant in vacuum. So this is not going to change, but these two will go. So which one has a higher frequency, violet or red? Violet has a higher frequency, so therefore has a shorter wavelength. Red has a lower frequency and therefore will have a higher wavelength. Make sense?
Yeah.
Coming to reflection of waves. Look at the reflection of waves. When waves reflect, what happens? Reflection of waves. there are two types of reflections. One from a fixed boundary. And the other one from a free boundary. Okay, here we go. I'm demonstrating that thing here. To make a boundary fixed, I'm holding it. That's it. I'm just holding this side. So that makes it fixed. What will happen to the waves as it goes and hits the fixed boundary? It will bounce back, but just see what's going on, okay? So watch this. I'm creating a crest. I'm creating this. And watch that as it goes and hits the other side. So I'm going to create a crest. What's the crest? What happened? It flips. Again, I'll show you once again. Crest flips and comes back as a trough. You get it?
Yeah.
So what happens from fixed boundary? It reflects and inverts. Like if I'm sending a pulse like this, when it goes and hits there, it will come back that way. So it inverts and reflects. Now what about this? From a free boundary. Watch this again. Now I'm not holding that side. Now it's free. Watch the same crest when it goes there. What happens to it? Watch that crest. Comes back as a crest. It won't reflect. Again. Crest, crest. You can write it down here. It reflects without inversion. So there are just two types of reflections, from fixed boundary, from free boundary. This is technically what you see. From a fixed boundary and a free boundary, this is exactly what you see. So when he was holding the slinky in his hands, that was a fixed boundary. When I sent the wave from here, it went and flipped and came back. You understand that? The same applies on a guitar string. When you pluck the guitar string, you're creating a crest. Goes there, flips, comes back, goes back again, flips, comes back. You should be able to do homework 3, and that's the last homework I'm going to give you all on this one. Homework 3. The next class we will be doing more about sound. So,
Are you close here?
there's no more test that's going to be here, but all these points will be included in the final.